So record is working. Yeah, so I think it's recording. All right, so yeah, so thank you all for joining. So yeah, so this as I wrote in the email that with some of you we are actually discussing this topic. So which is not so new, also not so old. So people are looking into this, let's say, at least last 7-8 years. But mainly you will find the high energy people are the initiative in that field. Then it slowly is moving to our domain as well as condensed matter domain. So we have started working on some project with Ujjalda, Priya, and Paranjoy, and Orko is there. So that's why we thought maybe, and yeah, with some of my MSc students, Rudraksh and Shobik, we also plan to do something. So that's why I thought maybe it's better to, let's say, have some introductory session at once. And then maybe if you have more discussion, if you wish to continue, we can have it. So again, so this is both, I mean, none of us who are working in this are expert in this field. So we are also learning something new. And many things are still not very clear. So there are many ambiguities are there. So the idea is to take this as a tutorial, but two-way communication. If you think something you are sure about something that you know something well, please speak about that and correct us. So it's not an expert talk. And ask questions. Okay, so that is particularly for the MSc students. So you have to at some point do the coding part. So keep asking the question. And we are initially planning to have 2 lectures, but we will see that if needed, we can have another one. So that's depend on how we proceed. Okay, so maybe, so let me introduce Arkaprava. So he's doing a PhD here with me. He joined last year here. And he's the one who has started mainly working on it and gained some insight by looking at the literature. So Orko, you can maybe slowly start, but again, keep the pace as much as slow, or time to time ask that whether it's slow, or you can yeah. So because this idea is that people should learn. Okay, so it's not a conference talk or a seminar. Okay, so Orko, you can maybe start. Let me.
Okay. Okay, so as sir said, this is something also very new to me. Maybe I have learned this in past 6 to 8 weeks, and there are many things that are still not clear to me. Like mostly maybe the motivation, how to interpret certain things, and there are many things like that. So if there are any questions, there is any question, please ask. And time to time, there will be certainly time when I will not be able to answer. Maybe if sir tries, then that is good. Otherwise, we have to again look into things. And I will mainly try to cover how to do the things. What is Krylov complexity? How it is defined, and how to calculate these things. The algorithm part, all those things. And in between, I shall try to explain what are the motivations, but I don't know how much I will be clear on that part. So, firstly, before going into Krylov complexity, I will start from some basic notion of complexity, not very concretely what is meant by complexity. So this is a whole subject like kind of thing. So there are many kind of notion. There are many characteristics how to define complexity in quantum computing and information perspective. So I will slightly tell about that, and then there is this Lanchos algorithm, which is apparently nothing to do. I mean, the motivation of Lanchos algorithm and Krylov complexity both are different, but Lanchos algorithm is the algorithm based on which we will find the Krylov complexity. So I could have done Krylov complexity separately without giving much time to Lanchos part. However, I will first try to formulate the Lanchos algorithm, because then it will be helpful to proceed easily in Krylov complexity part. So at first the thing is quantum computational complexity. So yeah, and at any point if you think there is something unclear, I am going too fast or too slow, I am explaining more. So please correct me. And if I say anything inconsistent, anything wrong, and I am sure there will be plenty of time like that. So please correct me. So quantum computational complexity. So without the mathematics or the proper definition, so the what it means by quantum computational complexity, so this is the complexity that arises when we try to approximate a quantum state from a given reference typical state by a series of operations. So it can be a state. So let's say we are given a very easy state which is psi naught. By easy I mean something maybe 000 kind of state or anything like that, typical state, and we want to go to a state, my target state, that is shy. So how can we go from shy not to shy? So is this process very easy or very hard? So if this process is very hard, we say the complexity of the state shy is very high. Similarly, we can also try to construct an operator. Maybe we have an operator u, unitary operator. So we need to formulate this operator to perform some operations. So how can we construct this unitary operator u from some basic local gates, not all local gates. So mostly maybe using C naught, H, and maybe T, S, this kind of gates, using how easily can we construct this U. So if it is very hard, then we can say the complexity is very high. And if it's low, then we can say the complexity is very low. So there are other kind of complexities also associated with these things, or what are called like Nielsen complexity. I don't know what it is, but I have found it many places. So there is this time complexity, how much time it takes uh, to go to my reference state or operator. There is size complexity, how much size do we need, maybe from computer memory perspective. So all these things are there. So Krylov complexity is something. So the main thing is whatever complexity I am saying, it should give me a number which will be associated with a higher value with the state or operator that has a higher complexity, and will be of a low value when the state or the operator has a low complexity. So Krylov complexity is also something like this, but how it is related to this, I will come to that later. So this is the complexity part. So now let's see how the Lanchos algorithm or this Krylov name comes into play. So the thing started around 1930 when two different physicists, different mathematicians, Krylov and Lanchos, both are trying to do something. However, they both had something different motivation. So what Krylov wanted to do is something like this. So So Krylov initial goal was to find a method for the efficient construction of secular equation. So secular equation means the equation that we sought to find the eigenvalue of a matrix. So So let's say our Hamiltonian or our matrix, it's not necessarily a Hamiltonian, but let's say it's a Hamiltonian. So, so H is our Hamiltonian. It is a Hermitian matrix, and it is over a d-dimensional Hilbert space. So what is the secular equation? So it is something like this. So this is the whole matrix, the Hamiltonian matrix. And to find its eigenvalue, what we do is subtract a minus lambda from all the eigenvalues, and then we take the determinant equal to 0, which gives us the secular equation. And by solving this equation, we find the eigenvalues lambda. So let's say this equation is the characteristics polynomial that this determinant gives. Let's say this is, we write this like this. So when we expand this determinant, we get a polynomial like this. So it is a, if it is a 3 cross 3 Hamiltonian, we get a polynomial in lambda of order 3. A lambda cube plus B lambda square plus C lambda plus D equal to 0, something like that. So this is a D order polynomial. So Krylov's goal was how to find this SK, these coefficients SK efficiently. So if you see, you cannot, by efficiently, what I mean is, by what Krylov meant was, he wanted to find this SK order by order. So let's say at first I find the coefficient of lambda, then the coefficient of lambda square, then the coefficient of lambda cube, something like this. But if you see the structure of the Hamiltonian, if you are asked, what is the coefficient of lambda to the power 12, you cannot say easily, because the minus lambda are all in the diagonal part. So we have to at first uh, expand the determinant, maybe whatever the d is, maybe d is 100, then you have to expand the whole 100 power polynomial, then rearrange that, shuffle that, and then you can find the coefficient of lambda to the power 12. So Krylov wanted to avoid this for numerical efficiency. So he proposed a method like this. So you choose a probe vector in the Hilbert space. So H is my Hilbert space, this curly H, and omega is, capital omega is any vector from that Hilbert space, a typical any generic vector. So we construct this set of states that are defined as omega, H acting on omega, H square acting on omega, like this. So using these vectors, I am not going into details. So it is like some 4 to 5 page algebra, but very easy algebra. It is like undergrad level algebra. So using that, I can show that this matrix, this equation S of lambda can be transformed into something like this. So this matrix was the thing to note is D cross D dimensional. So this can be transformed into a matrix like this. So there are other elements here.
So one question, please.
Hmm.
How you are transforming this by these vectors psi, hi,
Psi,
h,
you mean I
sorry,
have
sorry,
omega here.
omega, 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 h, omega.
So this is I have just a generic state from the Hilbert space, which is omega. H is a operator on the Hilbert space, the Hamiltonian. So I am just acting Hamiltonian on the state. So I will get a different state.
Is that okay? But this P of lambda, this matrix. So
Hmm.
you are transforming this above matrix to this. So by any unitary operator or something.
No,
So
not like this. So there is a whole. That's what I avoided actually here. So there is a this omega one, omega two that are entries in the matrix. These are some values, some expectation value kind of thing. So after a long algebra from this matrix S of lambda, I can show. So this is a D cross D dimensional uh, matrix. So this is not a unitary transformation. This is the D plus one cross D plus one dimensional matrix. So this is not some kind of unitary transformation from
acha,
that
acha.
S of
So
lambda
this,
to P of lambda.
so this is another matrix I can think, and which comes from this S
Yeah,
of lambda.
yes, exactly.
And this set, how many elements this set have? That's the
Yeah,
vector
yes, in
T.
principle you can have infinite number of elements in this because you keep on adding Hamiltonian there,
Hmm.
acting by Hamiltonian you get on different vector. But however, there will be a linearly independent kind of thing there. So so there is a bound on that. So that's also I am not discussing here. But
Acha,
you
acha.
can in principle go till infinity, but there will be a number that will only be necessary to construct this matrix. So this is not some very important part for our context,
Acha.
but I just tried to give a perspective here. So this is, I can expand like this: n equal to 0 to d pk lambda to the power k. However, here if you see, this is a d plus 1 cross d plus 1 dimensional matrix, where if you expand around this value, say lambda to the power 1 or lambda square, you will get a number. So it is just like expanding the determinant along the first column. So if you expand along this lambda square, that means I will remove this row and this column, and then I will expand the determinant. So I will get a number. So the thing is that number, what I get, that is P2. So if we expand around lambda square, I will get P2. So this P2 is equal with this SK. So this can be shown, these two are equal. Maybe up to a overall multiplicative factor, like the thing is this S of lambda and P of lambda, these are equal. So S of lambda is equal with some multiplicative factor to P of lambda. So previously the problem was I could not find the coefficient of, let's say, lambda to the power 7, lambda to the power 12 separately. I had to expand the whole determinant to find then I will have all the coefficient together. But here I can find the coefficient of lambda to the power 0 by expanding around lambda to the power 0. Then I can find the coefficient of lambda to the power 1 by expanding around lambda to the power 1. And these things are equal. So this was something else Krylov wanted to do with this. But the main thing that we'll use is this part, Krylov's method that I said. Ki I am taking a probe vector and I am applying repeatedly by h on the probe vector, and I am getting a set of vectors. So this is the essentially main part. So this is what Krylov wanted to do. So, and this is something same that Lanchos wanted to do. So some things that to note before going into the Lanchos part. So, so we are taking the probe vector omega. So I can always write this in the eigenbasis of the Hamiltonian. So let's say we expand omega as while lambda n are the eigenbasis of the Hamiltonian. So if we apply by h to the power k, k times h on omega, so what will happen? So for all the lambda, I will get a, so there will be a lambda in here. So all the eigenvalues will be multiplied k times. If I apply k times Hamiltonian, or in this expansion, all the eigenvalues will be multiplied k times. So in this way, I can see if, let's say, the eigenvalues, the lambdas are something like this. There is a order, say lambda 1, lambda 2, till lambda t, where I have arranged them in lowest to highest order. So the contribution, the lambda d is multiplied by lambda d to the power k, and lambda 1 is multiplied by lambda 1 to the power k. So the contribution of this is far, far greater than lambda 1 to the power k, because lambda d is very greater than lambda 1. So effectively, the highest eigenvalues are the one that contributes more. So the highest eigenvectors are the one that contributes more with more coefficient weight in this expansion. So this is something that will be helpful later. And the space that Paranjayda was saying, the number of vectors that I get by applying. So let's say this is the space that is spanned by those vectors, omega, h omega, h square omega, something like this. So this space is known as the Krylov space. So this is a space that is dependent on the probe vector. In this context, this vectors, and this is a subspace of the full Hilbert space. And the dimension of this space depends on the probe vector. So maybe I have a probe vector that is not spanning the full Hilbert space. Since this is a subspace, so the dimension, let's say the dimension is k. This k can be less than equal to d. D is the dimension of the full Hilbert space. So for mostly generic probe vectors, if I keep on applying, I will get a subspace that has dimension equal to D. In those cases, the Krylov space will be same as the Hilbert space, but there may be certain instances where the Krylov space will not be of the same dimension of the Hilbert space, but it will be of a lower dimension. And ideally, it can start from 1.
Hello.
So if I have a, yes,
I have a little doubt in
Hmm.
the matrix in the last slide, the no, the where you define that P matrix.
Yeah, okay.
Here these lambda 1, lambda 2 in the first row, this
Hmm.
lambda 1, lambda 2, lambda d, they are the eigen values of like after we are operating with Hamiltonian on this, right?
So these lambdas are not yet the eigenvalues. These are coming
Sorry,
from the lambda.
sorry, not lambda, these omega, sorry. These omega 1, omega 2.
No. Those are not eigenvalues. Those are not eigenvalues. Those are some expectation value that are taken in these states. This omega, h square omega. Those are, you can just consider those some numbers, some coefficient kind of thing. So if you want, so there is this thesis. This is the main reference I am using. So this is a very long and elaborated thesis. So it is available on archive. You can just search on Krylov complexity. So this is the first chapter and some first pages. So there is very easy algebra and you can find out what are these omegas.
Okay. And in the next slide, what, here only these omega n's are the eigenvalues for after operating H, right?
No, omega n are the coefficients. I have a state omega. This omega, I am expanding that state in the eigen basis. So this omega n are the coefficients. So I can expand any state in a basis set.
So how do you choose that basis set? Like
This is the eigen basis of the Hamiltonian.
for Hamiltonian. Okay.
Yeah.
Okay. Thank you.
So now let's come to the Lanczos part.
Hi. So in the
Yes.
note that you have written, so you mentioned something about the ordering of these eigenvalues with the
Hmm.
superscript k. Yeah. Can you mention that again?
Yeah. So let's say the set lambda, lambda 1, lambda 2 till lambda d, these are my eigenvalues, and I have arranged them in an increasing order. So lambda 1 is the lowest eigenvalue and lambda d is the largest eigenvalue. So when I am expanding, so let's say if I something like this, h uh, to the power, let's say cube acting on omega, let's say the omega is some, let's say my omega is like this, c1 lambda 1 plus c2 lambda 2. c1 c2 are the coefficients. Then I am applying h on omega. What will I get? c1 lambda 1 plus c2 lambda 2 lambda 2. This lambda 1 and lambda 2, those are outside, these are the eigenvalues. So if I keep on applying, so let's say I apply k times, then I will get c1 lambda 1 to the power k plus c2 lambda 2 to the power k. Now, if lambda 1 is much less than lambda 2, then what will happen? In the expansion, this will have very less contribution because this is multiplied by a lambda 1 to the power k and this has lambda 2 to the power k, while lambda 2 is very large number than lambda 1. So it's like this vector h to the power k acting on lambda is going to be almost equal with this one.
Right. Yeah.
So
Okay.
the largest eigenvalue having the largest the eigenstate that is associated with the largest eigenvalue has contribution more in this expansion.
Right.
So that's
If
what I wanted to mention.
when all lambdas are greater than 1, right? But if all
Yes.
lambdas are less than 1,
Now,
then
yes. Then the lowest eigenvalue will have largest contribution.
yeah.
Yeah, so the Lanczos algorithm, so Lanczos was also of a similar time around 1930, but his goal was to construct a way so that you can find you can approximate the largest or some lowest eigenvalue of a Hamiltonian. So let's say I have a 10,000 cross 10,000 dimensional Hamiltonian. So it will have 10,000 eigenvalues. But let's say I don't need all those 10,000 eigenvalues. I need only the highest 5 eigenvalues and lowest 5 eigenvalues. Or let's say the highest 10 eigenvalues or the highest eigenvalue. So how can we do that? I don't need to find all the eigenvalues. So that was the motivation of Lanczos. So he used a so he also used the same thing. So he also took a probe vector omega, and from this he created a set of vectors h to the power k acting on omega, or k equal to 0 to k minus 1. This k is this capital K is the dimension of Krylov space. So this space is called the Krylov space. So for this purpose, so how did Lanczos did it? So he he used this vector. So this is only the similar part, that Krylov also used this set of vector omega h square omega h cube omega for his purpose. Lanczos also used this set of vectors for his purpose. So what Lanczos did is the following. So I have this set of vectors omega h square omega, something like this. So using this, I can always form a orthonormal basis set using Gram-Schmidt method. So let's say I normalize my first omega. So this is, let's say omega, this is, let's say, normalized. Okay. So this is, let's say, One second. Yeah, so let's say, so this I name as like this: omega 0, omega 1, omega 2, like this set. So let's say my omega 0, that is the first omega, that is normalized by assumption, or at first I am taking the probe vector to be normalized. So let's say I will find a normal orthonormal basis set. So omega naught is the first element there. So how do we find the second one? So let's say we omega 1 minus omega naught omega 1. So this is just subtracting the contribution along omega naught. And if I then normalize this will be my second vector, right, in Gram-Schmidt process. So the third vector is like this: omega 2 minus, and let's say this I name as omega 1 prime. Prime means the normalized one. So omega naught yeah, so I have to subtract the contribution along omega naught and omega 1. So in this way, I form the usual Gram-Schmidt method, the set of orthonormal vectors. So Krylov did a modification of this formula. So he used as his base this Gram-Schmidt method, but he did some modification, and his algorithm was something like this. So the main goal is to find a set of orthonormal basis vectors from this set: omega, h omega, h square omega, h cube omega. So I am getting a set of vectors. Using those vectors, I want to find a set of orthonormal basis sets. For that, this is the following algorithm. So this is the starting step. Set k naught equal to omega. So this k are my normalized Krylov vectors. These vectors are called the Krylov chain Krylov vectors. So this is normalized. And then assign a naught equal to k naught h k naught. Then my second step, n equal to 1. So this is the algorithm part. So this is just like previously what I wrote. This second term is subtracting the contribution along the first vector, k naught. And so if the norm of the A vector is 0, then break. This means there is no linearly independent vector. Then set, sorry. So this is just like the normalizing part. My A1 was the H acting on K naught minus the contribution along the K naught vector, and then by dividing by B naught, I am just normalizing this, and I am getting my second orthonormal basis of the set that I am trying to create. So, and here also assign A1 equal to K1 HK1. So see, in the way I am constructing the following vectors K0, then I got my K1, and in the way I am also getting some numbers. This A0, then A1, here I have B1. So, and this is the final step that will be repeatedly done for n greater or equal to 2. And this is where the main advantage of Lancho's algorithm lies here. Set an equal to h minus so let's say here in this step when I am getting this a1, so a1, to get the a1 I just subtracted the contribution along k naught. So k naught means the only basis vector that is before this k1. So in Gram-Schmidt, what we do, if we let's say if we want to find the seventh basis vector, so I have to subtract all the contribution that are along the previous 6 basis vectors. So here, when I am trying to find the K1, so I have subtracted only the contribution along K0 because there is only one basis vector before that. So for greater or equal to 2, what I am saying, so here it means, here you see h minus a n minus 1 k n minus 1 minus b n minus 1 k n minus 2. So this a, so if I expand this like this, h acting on k n minus 1 minus a n minus 1 k n minus 1 minus b n minus 1 k n minus 2. So this is my equation. So see, I am only subtracting the so by h acting on k n minus 1, what do I get? So this is some order of, you can say kn, or let's say the omega. So this is like h to the power n acting on omega that I had, because the k n minus 1 already has n minus 1 h acting on the state, and here I am again acting another h. So this is effectively like this. So from that, I am subtracting the previous contribution, the coefficient of the previous two sides, the two basis vector, k n minus 1 and k n minus 2. If I am unclear, please say, because I also know that maybe I am not using the right words to explain. So the thing is, in Gram-Schmidt method, let's say if we want to find the 10th vector, 10th orthonormal vector, I needed to subtract the contribution along the all previous 9 basis vectors. But in Lancho's method, I don't need to subtract the contribution along all the previous 9 vectors. I need to make it orthogonal with only the last 2 vectors. So the 9th and the 8th vector. So that's why k minus 1, k n minus 1 and k n minus 2. So this actually makes sure that the thing is orthogonal with all the previous vectors. The construction is such that, so if you see, if you want to do something like this, this a n minus 1 and b n minus 1, the coefficient, if you do like, let's say c k n minus 3 minus d k n minus 4. So here this c d, if you try to find the coefficient, the value of this c d, this all becomes 0. So if you make orthogonal with only the last two orthonormal vectors, you ensure that this is orthogonal with all the previous eigenvectors. So this is the advantage of Krylov's method. You don't need to orthogonal it again and again with all the previous vectors. Is this part clear? Again, if you want to see how this is being ensured, just making it orthogonal with the last two vectors is ensuring it is orthogonal with all the vectors. You can see this thesis that I said, this on Krylov complexity. This is also very easy to check, but it is a 3-page algebra, but undergrad level algebra. Just making orthogonal with the last two vectors ensures that it is orthogonal with all the previous vectors. So then this is my an. So if an equal to 0, break. That means I have come to the point where there is no linearly independent vectors anymore. So what Paranjay initially said, that part, I can make all many vectors that I want, but I need actually the linearly independent one after this algorithm. So all of them will not be linearly independent. This part is similar like previous. So I am assigning Bn to be the norm of the An vector, and then I am normalizing An by Bn. So I am getting my Krylov vector Kn, and I am assigning An to be the expectation value of Hamiltonian in Kn. Then this is the whole algorithm that we have to do. So initially, I have my omega vector. So this part. So initially, I have my omega. I choose that to be not normalized, and I set that to my k naught. Then I assign a naught to be the expectation value. Then I subtract the contribution along the previous direction, and then assign this an and bn, a1 b1, and then for in onwards greater than equal to 2, I just keep subtracting the contribution along the previous two vectors. You see this a n minus 1 and b n minus 1, a b n minus 1 and a n minus 1. These are the coefficient that I found in the last step. Here I have found this b1 and a1. These two will be used in the next step like that. So in this way, what happens? I get a set of basis vectors. Output is like this of this algorithm. I get a set of basis vectors. The number of basis vector is k. I am starting the index from 0, so the upper index is k minus 1. And this k is 1 greater than equal to k less than equal to d. D is the dimension of the Hilbert space. And I am getting two set of coefficients, an, bn. So if you see, I have also found a recursion relation. So the recursion relation is, I was assigning kn equal to 1 over bn an. Okay. And 1 over bn my AN was, let's say from this step here, okay, so leave that for general, not that one. Yeah, this one. My AN is H minus AN minus 1 KN minus 1 minus BN minus 1 KN minus 2. So I'm just putting that here. H minus AN minus 1 KN minus 1 minus Bn minus 1 by Bn. This is the Bn. I am just expanding. Kn minus 2. This is my Kn. So you see the Kn is related to Kn minus 1 and Kn minus 2. So if I want to write the Hamiltonian in this Krylov basis, so what will be the elements? So this will be like this: Am, H, Kn. Let's say these are H, Mn. So now let's see what is H, M0. So what I am trying to do here is to write the Hamiltonian H in the Krylov basis. I can always transform basis. So in Krylov basis, how it will look. So 8M0 will be something like this: Km H K0 equal to Km. I am just writing H acting on K0 from my algorithm part. If you see there, it was like this: A1 plus A0 acting on K0. Right? Yeah, from this first line, the box one. A1 equal to H K0 minus this one. H minus A0 acting on K0. So H acting on K0 will be A1 plus small A0 K0. So this is what I have written here. A1 plus small A0 K0. So this is like this. Km. So A1 is B1 K1 plus A0 K0. So this is B1 delta M1. Because this K are all orthonormal. So Km K1. So this will be delta M1 plus A0 delta M0. So similarly, this was just using K0. I can find Hmn equal to Km Hkn. This will be so I have to just use this Kn from this equation. So here Kn equal to 1 over Bn An. I will write that, and then in place of An, I will write this one, and then I will use the just Dirac delta, Kronecker delta property, and I will arrive at this equation. And H M K minus 1. So this is the last one. Is A K minus 1 delta M K minus 1 plus B K minus 1 delta M K minus 2. So these three things, this This is 1, HM0, this is 2, HMN. These are all the elements, and HM, using these three, I can write the Hamiltonian in the Krylov space. So this will look something like this. A naught, B1, B1. So it will keep going on like this. These are all 0. So this is a tridiagonal matrix. So all the diagonal elements are the A coefficient, A0, A1, A2, A3. And there is this B1, B2, B3, B4. Those are just the above line of the diagonal and the lower line of the diagonal. So this is the Hamiltonian that I can diagonalize and find the eigenvalues to find the extreme eigenvalues. So in general, so yeah, so where I told about the dimension thing, so I can have as many vectors that I want. Let's say I can have like omega naught, omega 1. Omega 1 means h omega naught, then omega 2, till let's say omega are very large number. But when I make them orthogonal, all of them will not be orthogonal. Let's say I get this k naught, k1, k2. Let's say I have 500 orthogonal vectors, right? So this 500 can be the dimension of the Hilbert space D. So if that is the case, then this Hamiltonian in Krylov space also will be D cross D dimensional. Otherwise, it can happen. My probe vector was such that it could not generate D linearly independent eigenvectors, right? So maybe the algorithm automatically stops at, let's say, 300. So k naught till I get, let's say, k 300, right? Then this matrix will be a 300 cos 300 dimensional matrix. Other thing is, I have a choice to stop the algorithm. So let's say my Hilbert space dimension is 1000. I have choose a probe vector omega such that it can in principle generate 1000 linearly independent vectors. So the dimension of the Krylov space will be equal with the dimension of the Hilbert space. But I don't want to construct the full space. So in my algorithm, where I was this increase n to n plus 1 and repeat the current step, in this case, I can stop it at any point that I want. So I will get a set of vectors. So let's say for a case, I stopped at 200. So I have 200 Krylov vectors and I construct this 200 cos 200 dimensional matrix. So this is the final output of Krylov. If I diagonalize this matrix and find the eigenvalue, I will see only the largest eigenvalue and the lowest eigenvalue are almost equal with the original eigenvalue of the Hamiltonian. So this Hamiltonian H, let's say original Hamiltonian H had eigenvalues like this, original, lambda 1, lambda 2, till lambda 1000. So in my case, I am approximating till my desired approximation level. So in my case, this H prime, or let's say this H omega, means this is the Krylov space. I am getting lambda 1 prime, lambda 2 prime. These are in increasing order. And this is, let's say, till lambda 300, right? So I will see the first 3 or 4 eigenvalues and the last 3 or 4 eigenvalues will be almost equal with the first some eigenvalues here and the last some eigenvalues here. This is the inherent property of the Lanchos algorithm. So if I want, I can construct the full matrix, this full Hamiltonian. So my D cross D dimensional Hamiltonian, I can construct a D cross D dimensional Hamiltonian in the Krylov space, and I can find the eigenvalues. And most probably, I'm saying most probably in that case, all the eigenvalues will be equal with this eigenvalues, because I have just transformed. This is some kind of basis transformation. There is no approximation. If I keep all the dimensions same, so this is just a basis transformation. However, this looks easy, and for my so if I want to find only the largest eigenvalue, I can see. I mean, if you do this algorithm, implement this algorithm, it will be like, maybe if I only construct 50 cross 50 dimensional Hamiltonian, so I cut my algorithm at n equal to 50, so maybe that will be sufficient to approximate the lowest eigenvalue lambda naught. So I have to put some kind of check there. I have to somehow ensure what is the approximation level. So only if I need the ground state eigenvalue or the highest excited state eigenvalue, I don't need to diagonalize and diagonalize the all H 1000 cross 1000 matrix. I can only diagonalize the 50 cross 50 matrix constructed in this way to find the eigenvalue, the lowest eigenvalue. So this is the main Lanchos algorithm part and the benefit of Lanchos algorithm.
Hello,
Yes.
can you repeat what you said earlier about this upper bound on the omega part, like omega 10,000? How do you get some sort of idea like where it will stop, that 10,000 number?
Yeah, so that will stop using the Gram-Schmidt method, the Lanchos algorithm part. So in usual Gram-Schmidt, what happens? So let's say I have these vectors. I have, let's say, psi1, psi2. These are all linearly dependent, not independent vectors. Psi3 till, let's say, psi 1000. So I am given these vectors, but let's say it is in a 100-dimensional Hilbert space. So obviously these are not orthogonal vectors because I cannot have 1000 vectors there. So if I start my Lanchos algorithm, I will get, let's say, these are my orthogonal vectors. Phi1, then I get phi2. Where phi2 means I am just subtracting from the contribution along phi1, then phi3. So the Gram-Schmidt, usual Gram-Schmidt algorithm is such that it will automatically stop at phi 100. So this is the Gram-Schmidt, because Gram-Schmidt cannot produce more orthogonal vectors there, right? So similarly, Lanchos algorithm also take care of this thing. So if my Hilbert space dimension is, let's say, 1000, this is my D, but I produced omega, H omega, H square omega, till, let's say, H to the power 2000 omega. So I am starting with this list, and I start the length.
How do you know that? This only I was asking. How do you like know ki we have to go to H2000 only? Like if I want to do it numerically and like see ki
Yeah, so you don't, that if you see in the Lanchos algorithm, you are not starting with this whole list. It's not the input in the algorithm. So you only have omega. So from that you go H acting on omega, and here you get K1, right? This gives you K0. Let's say this is K. So from this K1, you apply again H acting on K1 and do something. From that you get K2. Then you apply H acting on K2, then you get K3.
Achha.
The Lanchos algorithm follows like this. There will be a time when you will see H acting on Kn, you cannot go to Kn plus 1. That is how it will break. It will break from this condition.
Okay.
Root over an equal to 0, then break. So this an means the next linearly independent vector that I am trying to create has a norm 0. What that means? All the linearly independent vectors have been created. So this way there is a break in every state. Okay. So in n equal to 1, you see there is a break. If the norm of the vector is 0, then break. That means there is no more vectors. If norm of n is 0, then break. It means there is no more linearly independent vector.
Okay.
So,
What
so
is the reason? Hello.
Mhm.
What is the reason that this truncated Hamiltonian in Lanzos basis it can approximate the eigenvalue at the edge of the spectrum?
Yeah, so that has something to do with what I said at first. Okay. So this thing here. So
But
when I
then
am
it
applying,
was, yeah, but this was only for the basis of H, multiple H acting on this probe vector,
yeah,
whereas
so
the
I
field,
exactly, but I cannot actually give some more light on this, but I cannot explain. I have seen this. This is also in the thesis, but the explanation would require some more mathematics and some more things that I am not very much aware of. However, this does approximate. This is the result. So if sir can say anything, why does this approximate?
So this usually, I mean, whatever I know, this is basically, you can hear me, right?
yeah, I can hear
Use
you.
the headphone, maybe otherwise background noise. Just give me 1 minute. Yeah, usually the basic principle, I think whatever we explain is that one, this is a powered law method. So if we keep on applying again and again, then the extreme eigenvalue will be the remaining one, or the one which are with highest coefficient that will survive. And this extra orthogonalization actually makes this process faster. So if we don't generate this kilo basis, I mean, in terms, so there are two aim. One is to generate kilo basis. We'll understand the complexity, that Orko will tell more about that. But you will see that the current package that you use for diagonalization, that also has this Lanczos method, where the goal is to find out the low energy states. And there, the basic principle is that if you keep on, you can represent any state in the eigenbasis of the given Hamiltonian. And if you keep on applying the Hamiltonian again and again, it will ultimately converge to the subspace which has highest, or you can say the lowest spectrums, or the extremas. And this intermediate orthogonalization helps you to reach to that subspace faster. That is basically the powered law story so far I know. And this you will see, can try if you have done Lanczos at some point, you can see that this really works. Because when we were actually 10 years, 12 years back, so when I was just started the PhD at HRI, so that time actually our first project was to develop this Lanczos code. So this business was there for some long time. But now this Krylov interpretation is basically something that people came up that in terms of complexity. But Lanczos is very familiar to, I think, many of you as well. Okay, so this you can maybe, there are good literature as well on only for Lanczos. But this convergence to this extremum lies on mostly the success of so this is a variation answer. So you'll see this kind of thing appears when we talk about Hartree-Fock, all these things. That whenever there is an optimization, if you keep on somehow applying the cost function, then it essentially leads to some subspace. You cannot reach the whole spectrum, but at least you can talk about the extrema thing. So that is roughly the
But it is not still clear, right? Like if you just keep applying Hamiltonian, then you'll generate some subspace, like
right.
at till the point when it becomes zero, the next vector, right? Something like that. And those are like some vectors. And in terms
Yes.
of that, as he explained earlier, you can see
Mhm.
that because all the like higher vectors come with the higher powers of lambda.
Exactly.
But when you do this Lanczos algorithm, then the
Mhm.
vectors are no more just these towers of the Hamilton eigenvalues times the probe vector, but those are more complex linear combinations of those. So
Exactly.
it's not very clear just by looking at them why this should happen.
No, I
But
mean,
you're saying that in practice it does happen.
yeah. So if we go back, or if we go back to this power law thing once more. So if I'm getting you right, the starting point. So this you agree,
This
right?
part.
This you agree, right? So if I,
Yeah.
so you
If
can
just have
see
h power k omega.
exactly. So you see that it will ultimately converge to lambda 0. Let's say, or lambda highest. You can change the sign of the h. Let's say if lambda maximum, the highest lambda is lambda maximum. So ultimately all the others will die out, and you can approximate the k time, the state you can generating after k time application is basically the one which has highest eigenvalue. This part is right, clear, right?
Yeah.
So this addition, so this again, so there will be, it not be perfect or it may take more time. So what they say is that if you, as an intermediate step, if you keep doing this orthogonalization, that actually helps you to reach to that subspace faster. Okay, and in between, you not only reach the exact highest or exact down state, but some of the previous steps are basically corresponding to the states which are close to the ground state or close to the high state exact state. Okay, so that's why it's not a single, it is not converging to a single. So ultimately, what you have to do, ultimately, this basis will generate a tridiagonal matrix, and then you have to diagonalize it to get the ground state or the excited state. Okay, but this does not only converge to a single state, rather couple of excited states also you can get the value quite well. Okay, this you can play. There are Langeau subroutine app available, I think, so this you can, it's very easy to just Gram-Schmidt and application of small Hamiltonian. This you can play and see that why this. So this is basically, there is no, I mean, this is of course a hand waving argument. I cannot prove it, but you will see this kind of argument comes when we talk about this variational ansatz, where we have to optimize over many parameters. So this works. You will see this kind of thing in other contexts as well.
Okay. Thanks.
So one thing maybe I want to ask Orkos, what is your immediate plan now? So from where you want to go, because we have already crossed 1 hour. So
Yeah, so I was just going to take 10 more minutes to just introduce the Krylov state complexity part, because the basis generation is done. So this is just 5-minute work. And from that part, I was thinking to do on next day.
Right. So maybe and 5 minutes we can also keep if somebody needs little revision. So you can end this thing with a little, let's say, a very brief summary that whatever we targeted today.
Yeah, okay.
Okay, so that will
Okay,
be
then let me just take 5 minutes to just introduce the Krylov state complexity.
Yes.
It will take just 5 minutes, and then I will just again summarize what we have done so far.
Exactly that.
So 10 minutes.
Yeah. Okay.
Yeah. Okay.
Thank you.
So one thing is, so what I said, I don't need to construct the full Hilbert space dimensional this Hamiltonian to approximate the lowest eigenvalues or the highest eigenvalues. So so the thing is, in the Krylov, this what I am trying to say is this Krylov method is not numerically stable. So this is something that I did not know, and I faced it while coding. And so what happens is, normally when in an algorithm, when in a theory we have something like zero, where something should come as zero. In this Langeau's algorithm, not Langeau's, in computer language, it normally comes a very small number, like 10 to the power minus 16 kind of number, depending on the precision. The Langeau's algorithm is such that this 10 to the power minus 16 adds on very quickly. So when you keep on running the loop, maybe you should get somewhere zero on every loop, but you will get zero on the first. You are getting 10 to the power minus 16 on the first loop, then maybe 10 to the power minus 15, then 10 to the power minus 15, then 10 to the power minus 14, like this. So after, let's say, maybe 50 or 100 step, you are getting 0.001 kind of thing, where you should have you should have got 0. So this actually brings the instability in the algorithm. So for the Lanchos motivation, what he wanted to do was find the largest eigenvalue or the lowest eigenvalue. For that, I do not need to construct the whole Hilbert space dimensional this Krylov tridiagonal matrix. So in that case, maybe I am stopping before this numerical error accumulation happens. So maybe this will happen, let's say at 500 step. But for Lanchos purpose, I am stopping at 100 step, because this is giving me find my largest or lowest eigenvalue. So there I don't need to do anything. This numerical instability is not hampering my goal. But for the perspective of Krylov complexity, what I need is mainly the Kn basis, and I need all the bases. So for my a typical generic vector probe vector omega, I need to find all the Krylov vectors that can be produced. So in general, I will see this K in the dimension of the Krylov space will be equal with the Hilbert space. K is equal with D. I will come to into this more detail later tomorrow. So let's say my Hilbert space dimension, even for if it is 12, L equal to 12 for qubit system, my Hilbert space dimension is 4096, I think. So this is a large number. The numerical error will accumulate much more. So there are two remedies. One is full orthogonalization. So it actually kills the the numerical improvement that Lanchos algorithm gave. But for my perspective, for our perspective, we need the vector. So it is the price we have to give. So one is full orthogonalization. It is called FO. And one is partial reorthogonalization. This is full, yeah, Ananis. This is called PRO. So again, you can find these two. I am not going into detail. So these two you can find on the thesis on Krylov complexity on that thesis in detail. So it will make the code slower, because effectively what we will do is, in what I said in Lanchos method, I was just making it orthogonal with the last two vectors. But in Gram-Schmidt, I make it orthogonal with last all the vectors. So full orthogonalization is just I do the Gram-Schmidt method. I make it orthogonal with all the previous vectors, but not exactly Gram-Schmidt in a Lanchos framework. So there is some modification. So here also the output is this Kn basis sets and this An Bn, and this partial reorthogonalization is something that is more faster than the full orthogonalization. So I don't make each vector orthogonal with all the previous vectors. I check time to time whether the numerical error has been accumulated enough, so that I need to do something. I need to make again orthogonal with all the previous vectors. So there is a checking factor there. So I do orthogonalization, but time to time. So this is a more harder one, but this is numerically faster. So this is called the partial reorthogonalization. So these things are not needed for Lanchos purpose, but for Krylov complexity purpose, my main thing that I need is to find the Krylov complexity is this Kn vectors. So for this perspective, for this purpose, I need the this partial reorthogonalization or full orthogonalization implemented. So very briefly, I will discuss about this Krylov complexity of state vector that I am going to say now again tomorrow. But just to introduce, the main goal of this talk is Krylov complexity. So Krylov complexity can be of two types. One can be state complexity. One can be operator complexity. That I said at first, there can be state complexity. If I have a state, how complex it is to prepare. If I have an operator, how complex it is to prepare this operator using some local gates kind of thing. So at first we will start with state complexity. So very briefly, I will introduce, just say within 2 minutes, state complexity. So let's say I have an initial state phi of 0. So if I want the time evolved state, I can do this. Phi of t equal to e to the power minus iht acting on phi of 0. This will give me the time evolved state phi of t. So I want the Krylov complexity of this state, this phi of t. This is my motivation. And plot the complexity versus time. So my whole goal will be like this. This will be the Krylov complexity, and here it will be time. And my state will be this phi of t starting from 0. I want to plot the complexity. Okay. So for this, I will do the following. Using this phi of 0, let's say I write this phi of 0 as just phi. So using this phi, I will find the Krylov vectors. That's it, using the Lanczos algorithm. So what we did? So again, we have to just phi naught. So yeah, phi, just phi, then h phi, h square phi, something like that. I will find the, and using this, I will do the Lanczos algorithm. I will get k naught. So just in place of omega in the Lanczos algorithm, I am putting this phi. I will get k1, I will get k2, something like this. Okay. And then I can expand this phi of t equal to e to the power minus iht phi of 0 equal to, from this part, I am just introducing a complete set n equal to 0 to k minus 1. So this is identity complex set, because this kn are the are basis vectors. Phi of t equal to n equal to 0 to k minus 1. So this is like a coefficient. So let's call it phi n of t kn. So I am just transforming this phi of t into the Krylov basis vector set. And this phi n of t, this gives me the coefficient for each kn, right? So now let's define our operator q equal to sum over n equal to 0 to k minus 1. N is the integer, kn. So this is my operator, right? So Krylov complexity often denoted as ck of t is sorry, phi of t q phi of t. So the expectation value of this operator q in Krylov complexity of state phi of t is defined as this. The expectation value of the operator q in this phi of t state. This, if I just put the value of q here, I can see it will be like this. Sum over n equal to 0 to k minus 1 in mod of in of t whole square. So this is the quantity. So the whole goal is, if I am given to calculate the Krylov complexity of a state and plot maybe the time evolution versus Krylov complexity. So let's say this is my initial state, and I want to plot the Krylov complexity of this state with the time evolution. So using this state, I will find the Krylov vectors using Lancho's algorithm, K0, K1, K2, all these vectors. And then I'll time evolve this state phi of 0 to phi of t, and I will expand this phi of t in the Krylov vectors. So that will be, the expansion will look like this: n equal to 0 to k minus 1 phi n of t k n. This is just regular expansion. If I have a vector in a Hilbert space and a basis in a Hilbert space, I can always expand the vector in that basis. So this is just the usual expansion, and the Krylov complexity is defined as sum over n equal to 0 to k minus 1 n. So there is an integer multiplied mod phi n of t whole square. So this is the Krylov complexity. So just in 1 minute, so why this, how the complexity notion is coming here? So initially I said, when we have a state, how hard it is to prepare the state, that tells somehow the complexity of a state. So if I have a operator, how complex it is to prepare this operator tells us the complexity of the operator. So in this context, if I see the time evolution of a state, so phi of t equal to e to the power minus iht phi of 0. So if I expand this, if I expand the exponential expand the exponential, I will see that phi of 0, then I will have h acting on phi, then I will have h square acting on phi, all these terms. So this is the how the expansion will look like with some coefficients. So see, these are like the Krylov vectors that I used. So phi of 0, h phi of 0, h square phi, and there is a t associated, t square, let's say h to the power 10, t to the power 10 phi, right? So at a larger t, when t is very high, so this t to the power 10 will have more weight in this expansion. So having that means h to the power 10, this phi has more weight, this vector. So this n is because of that. This phi n is coefficient of h to the power n acting on this phi naught. That was giving me the kn, right? So I am multiplying a n. So this quantity will be larger when n will be large, and n will be large when the coefficient that is multiplied with n is large. So let's say it is like this: 1 multiplied by, let's say, 0.001 plus 2 multiplied by, because these are coefficients, so it will be normalized less than 1, 2 multiplied by 0.002, something like this. So let's say I have 10 multiplied by 0.01. So I am seeing that this is very low, this is very low, but 10 is multiplied by 0.01. This is high relatively. So this value will give me a higher value than if I have 1 multiplied by, let's say, 0.5 plus 2 multiplied by 0.2 plus something like that, then 10 multiplied by 0.00001, something like this. So this is higher than this one. So this is higher means this 0.01 is associated with phi 10, that is associated with k10. So this k10 is much inside this chain, right? So in the time evolution, k10s come after h to the power 10 acting on this phi of 0. So this is much more complex than h acting on phi of 0. So in that notion, if Krylov complexity is, the value is higher, then we can say the higher power of the Hamiltonian acting on the state has a higher contribution here. And it has more, actually what I said is very minimal in this context. Exactly how it means a complexity, that is something different. So I also have some confusion there. However, this is really very basic thing. I mean, very basic understanding of mine. This is how the complexity notion comes here. Yeah, so this is all I had to say today. And so just to sum up, so initially, uh, so the main thing is Lancho's algorithm. I can just start from Lancho's algorithm. That is the main starting point. So for Lancho's algorithm, I have a Hamiltonian belonging to a Hilbert space. I take a probe vector that lies in the Hilbert space, and that using that probe vector, I create I do the Lancho's algorithm. So the input in the Lancho's algorithm is a Hamiltonian and the probe vector. And the output is a set of Krylov vector, coefficient an, and a coefficient set bn. These a and bn coefficient sets are important for the Lancho's purpose to find the extreme eigenvalues of a Hamiltonian. And what we need is this kn set. So so my goal is I will be given a vector and a Hamiltonian. Using Lancho's algorithm, I will find these Krylov vectors. And when I have the Krylov vectors, I can find the complexity of a state. So the complexity of state means I have phi of 0. I have time evolved state phi of t from that phi of 0, which is e to the power minus iht phi of 0. And I can expand this phi of t in this Krylov basis. So phi of t is sum over n equal to 0 to k minus 1 phi n of t kn, just expansion. And then using this phi n of t, I can find sum over n equal to 0 to n minus k minus 1 n phi n of t mod whole square. This is my Krylov complexity. So for each phi of t, so with increasing t, I will get, so this is t, this is ck. Ultimately, we can see what we will see on the next day is we'll get normally we get a plot like this. So this is, let's say, t equal to 1, 2, 3, 4. For each t, I find a ck, a single value. So for each t, I keep on plotting. And initially, the complexity grows and then it saturates. So there is meaning for that interpretation, all those things. So yeah, this is all. If anyone has any question or Sarah has anything to say.
In the definition of complexity, so instead of n, if we would take any monotonically increasing function of n, it will still have the same interpretation, right? So the choice of n is it just a convention, or is there any more reason than to choose n and not some other?
I think this is the most easiest choice. I think most natural and easiest choice. Yeah, if you take any monotonically increasing function of n, that should also do the same job, but that will be unnecessarily complex. The most easier function built upon m that is monotonically increasing, that is n itself. The function is n. So I think that is the reason.
Yeah, and another probably, have you shown this, how to say this, tight binding kind of picture, Orko? Are we there?
Yeah.
Yet? Yeah, just go back. So then I think I can add to that. So
This Hamiltonian.
exactly. So this we can think as if those who are familiar with this tight binding or 1D, let's say physical, let's say model where you have a hopping between this nearest site. Okay. So you can consider basically this is one kind of, so this tridiagonal matrix, you can consider the diagonals are basically a particle is sitting at some site, and this extra additional diagonals are basically it is moving to its nearest neighbor sites. Okay, this is a kind of hopping model. Okay, so you can think this n and mod of phi n square is basically computing your average position. So you are letting the system to hop many sites. So how much it has on average moved in that lattice. So this is a kind of comparison you can give that expectation value of this n. N is basically, you can consider the expectation value of some position operator. Okay, so in this way, this is also kind of motivated that this n fine square is giving you some diffusion kind of thing, how much it has diffused. So that's another reason people consider it as a measure. But again, this origin goes back to this complexity theory. But as you mentioned, you can come up with another measure that works as long as it is a valid complexity measure, that should work fine.
Thanks.
So yeah, if again, so this complexity, maybe he will repeat because it's already quite long. Maybe you have lost some attention, so it's quite natural. But so he will start this thing again tomorrow. So, but if you have any comment on the pace, is it is fine, or we can make it a little faster? So you're always welcome to study. I mean,
Yeah, I can go faster or
yeah. So
slower.
this
What
is up to you. So
I
that.
think pace is fine. I mean,
Right.
as
Okay. Okay.
mine-
Okay. Because try to understand this thing, even if you're not working now, maybe if someday you are planning to work on this, at least these basics will be helpful. Okay. So that was the main purpose for, majority of it. So yeah, we will again come back more on this at the same time. So we hopefully have this recorded version, and in between he will share this handwritten thing that you have, right? Or I mean, you can
Yes, yes, I
just
have that.
share, maybe if not today, tomorrow we will try to share. And also maybe you are while you are writing, it's already getting saved, right?
Yeah, this is safe, but this is not very well written. But yeah, I can share
But
this
this
one
is also,
also.
I think, so that, and if you have
Yeah.
any better explanation about anything, please come back tomorrow and let us know. Okay, so that is always because
Yeah,
this
and
is
tomorrow I will start from the Krylov complexity part. So today mainly the Lanchos and the Krylov's motivation, all those kind of things are there. So I tried to cover those. So next day I will start from the itself from the Krylov complexity, and I will repeat the state complexity, and then if possible I will go into the operator part.
all right. Okay, then maybe let's thank the speaker and let's meet tomorrow again. Okay, thank you so much. Okay. Bye, everyone.
Yeah, okay.